Have you considered why we study conic sections together? Circles, ellipses, parabolas, hyperbolas. Although they do come from one object, the cross-sections of a cone, all of these definitions of the conic sections seem so random and are not connected at all. Now, watch today's video to see a connection algebraically of conic sections that you will not forget for the rest of your life. Hello everyone and welcome to another episode of Interstigation. In today's episode of Interstigation, I think this video is very good. I searched up the internet, there are very few good videos talking about this. So if you enjoyed today's video, I'd ask you to share this with your friends and subscribe to see more of these type of videos. Alright, let's take a look. We want conic sections. However, none of the definitions that we see normally make any sense when you put them together, when you study them together. For example, if we see, okay, the first thing we learn, circles, there is a center and the collection of points on the plane such that the distance from that point to the circle is the same, r. And then when we study a little bit more mathematics, we find, there is a close neighbor to circles. We call them ellipses. And ellipses have two foci, and each of them, we define an ellipse as the locus of points such that the sum of these 2 points, the sum of the distances to both of the foci stay constant. That is how we define ellipses. And if we study math a little bit more, we find, now we have hyperbolas. Hyperbolas are the curve where points such that the difference of these two sides are constant. X minus y is equal to some constant, technically the absolute value, in order to generate both pieces of an hyperbola. Now we brought up parabolas again. Parabola is something that we learned very early on in our mathematics career, and say, parabola is just something defined by a quadratic equation. Say y is equal to ax squared plus bx plus c. But that doesn't fit into this definition of conic sections. So we say, now we're going to define parabola in a new way, an inventive way. Now, let's say a parabola is now defined as the set of points such that there is this one focus and one directrix such that the distance from each point on the parabola is equal to the distance to the directrix. We say these two distances are the same. But these four definitions are still kind of far apart. I guess you could say that, circles and ellipses are connected because, if you put the foci of an ellipse close as possible, you kind of get a circle. And, the parabola and ellipses are kind of connected, but you don't really have one definition that connects all of the conic sections together, which does not really justify our act to talk about conic sections as a whole. We study conic sections as a whole for its amazing properties, but algebraically it does not make sense. So today, we're going to try, at least, to derive a formula that works for all of the conic sections. So let's get started with our parabola. So we see there is a focus and a directrix. So none of the other shapes actually have seemingly a directrix. What's that all about? In order to unify all of the definitions into one, at least we need to make sure that, okay, the directrix and focus should both exist, right? So, now let's take an ellipse. Let's just take a look just at this focus. Now there's another one on the other side, but let's just pay attention to this one focus. So the definition of a parabola is that the distance from the point to the focus and to the directrix is the same. So how can we kind of mimic a similar definition for an ellipse? If you can see, around this point, its behavior looks a lot like a parabola, even though it is not a parabola. So, let's think. Maybe we could put a directrix here where a parabola should lie, a directrix of a parabola should be. We usually say this is A, this length is B, and this length is C. Now, because for a parabola, we think, these are the same. Of course, these two distances cannot be the same anymore, because if they are the same, it's just going to be a parabola. So, maybe we can look at their ratio. This ratio, x over x, is equal to 1 in the case of a parabola. Let's take a look over here in the case of an ellipse. Let's just take some special points. So, let's see if we have, this point over here. So we have this distance over here to this distance over here. Let's just call this distance h for now, because we don't really know how far this directrix we should place it. But we know this is a minus c. Let's think about another point. How about let's pick this point? These points are easier to deal with. We know this distance to the directrix. Now we know, okay, this part is h, this part is a, so the distance must be a plus h. Okay, how about the distance from the focus to that point? That point should be a, because we know by our general definition, or more regularly seen definition of an ellipse, this should be length 2a. One side would just be length a. So now we want this ratio to stay constant. So maybe there is a constant that we can always take that, maybe we can make this some sort of constant. Constant, I will use k because we already use c. Okay, let's multiply both sides, try to solve for anything meaningful. Okay, do we get anything? Not really, but is there anything interesting that we can get out of this? Maybe, okay, let's try one more point. How about this point over here? Let's say this point, the distance to the focus is, that's a plus c, and the distance to this directrix that we set up is this a plus c 2a in the whole length plus h. So this distance is going to be 2a plus h. Okay, that's basically the same thing that we have over here. So that's not really helpful. So we must get something out of this. How about let's factor this as c times a plus h is equal to a squared. Okay, that looks kind of similar to this fraction we have over here. So a over a plus h, let's just make this fraction. Leave everything else to the other side. C over a. Okay, now that looks better. So if we have c over a, then that constant k must be equal to c over a. Does this ring a bell? It's the definition of eccentricity. How could I forget? It's actually just eccentricity of k. So, we can actually just define this directrix such that, maybe that the distance from each point to the focus divided by each point to the directrix is just the eccentricity. I won't technically prove it here for every single point on the ellipse, but that actually would generate this exact ellipse if we just change our definition a little bit to one focus and one directrix, and that the distance as a ratio from the point to the focus divided by from the point to the directrix is eccentricity, then you would actually get an ellipse. Let's see if we can replicate that idea in a hyperbola. Maybe I think our directrix should locate right around here. If we want to just set that, okay, let's say this is the center, then we know that this distance is A. We know that somehow there's some B over here, and, my bad, this distance is not A. And that this distance right here is A, and this larger distance is C. And there's a B such that A squared plus B squared is equal to C squared. Okay. Now, does this same definition apply? Let's try that. E is equal to C over A. It's greater than 1 right now, but let's just pick a point. Let's pick this point. Let's think. The ratio from here to here. And here to here. Is actually, we can define it so that this line, the ratio is exactly the eccentricity, and it would actually generate a hyperbola. Alright, so this definition that we just discovered over here actually applies to basically every conic section. Well, we didn't talk about circle really, but a circle is just a special case of an ellipse where two foci actually coincide with each other. So we can just ignore that for now. Okay, so we now have a general definition of conic sections. That is, for a general conic section, we have a set of points such that the distance from the point to the focus divided by the distance from the point to the directrix is constant, that constant being the eccentricity. Okay, now we can deduce kind of a corollary that we already know, that if the eccentricity is equal to 0, we have a circle. If the eccentricity is between 0 and 1, we have an ellipse. If the eccentricity is exactly 1, we have a parabola. And if the eccentricity is greater than 1, we have an hyperbola. Okay, that's very nice. So, how can we generalize this into an algebraic formula now? We want the algebraic formula. That's what we were here for. So, let's go back and take a look at how can we make this algebraic. So, we have to deal with a lot. When I mean a lot of distances, which is not very friendly in rectangular coordinates, because for every distance you need to find, well, basically use the Pythagorean theorem every time, find the square root of x squared plus y squared every time, which is annoying. So we turn to our good old friend, polar form. Okay, so let's take a look at our problem in the polar form. So we have the pole over here. What would be the most convenient way for us to define this? Okay, I think the most convenient way, because we're going to say the set of points, not x, y anymore, we are, yes, that's right, r theta, because we are in polar coordinates. Let's label that. Okay, now let's think. Where do we define the pole? We define the pole in order for us to simplify our definition a little bit, because we have to deal with distances. Distance to a directrix is relatively easy because it's either horizontal or vertical. We don't consider rotations yet, because for rotations, we can just rotate the theta a little bit. So now, I think it's the easiest for us to put the focus at the origin so that we don't have to worry about that distance part as much. So the distance from the point to the focus is just r. That's very easy. So now let's consider a directrix. Let's say with the formula in rectangular x equals negative any number h. Then this distance over here is going to be r, that's theta, r cosine theta, and this is h. So now, equivalent condition we're saying is r over h plus r cosine theta is equal to this mysterious eccentricity. Great! So r is equal to eh over 1 minus e cosine theta. So that is actually what we have for the general form of conic sections. So we can plot it into decimals. Take a look. So if I vary this e over here, you can see it turns from a circle to an ellipse to a parabola and finally a hyperbola.